we're now recording. My apologies for not filming earlier. But we do have the whiteboards, as you will see. There they are, waiting for you patiently. Okay. All right, so we're on this problem number 8 on the homework. And what we want to do is we want to say, what do we make of this? What do we make of this particular problem? So we have two curves, and we're asked to find the area of the region that's between these curves, whatever that means. So we have to, get a feel for what it looks like. Now, I could go to Desmos and graph them, and let's say I just do that to get a handle on the situation. So I go to Desmos, and I graph these things. The first one is y equals negative x squared. And by the way, since this is negative out front and it's a squared, I know that this is a parabola that's upside down. So I know that already. I don't have to graph it. I know that. And in fact, I could even recognize, I can factor it and see where it touches 0. It's going to hit at 0, and it's going to hit where? Well, it's going to hit at 0. And then when I factor out an x, I realize it's going to hit at 3, right? So when I graph that, I expect to see that. So there it is. Just like I had predicted, this thing is an upside down parabola that intersects at 3 and 0, like I said. You cool with that? All right, now, the other guy is a cubic. And I remember that cubics that have a positive leading coefficient look a certain way. So in my mind, I have a feeling what this is going to look like, but I'm going to graph it anyhow. And then I'm going to show you how I could have reasoned things without looking at the graph. So this is 2x cubed, okay? And then this is minus x squared. That's a brute. And then this is minus 5x. Oh boy. Well, ain't this something? So what I'm going to do now is I'm going to zoom out because I don't see what's happening here. And then I see, oh my God, this thing is a very sort of complicated creature. However, what I do know is I know that there is a region here, and it's actually going to require 2 integrals. Because if I look at this picture, I have this region in the negative part here, where the blue curve is the top, correct? And then over here, the region has a red curve as the top, and the blue curve is the bottom. Is everybody understanding that? So the first thing we're going to recognize is this creature is going to need 2 integrals. Remember how we defined area of these types of regions. It's the upper boundary minus the lower boundary. So for the first region, it's from here to here, the blue's up top, and then from here to here, the red's up top. And so you might say, okay, well, how would I have known this without a calculator? Well, you do have a calculator, and you could also have found these important points using some algebra. So even if I didn't have Desmos, I could have reasoned this picture just using what I know about polynomials. Let me show you why, or how, I should say. Before I leave Desmos, does anybody have a question? Now remember, you guys live in 2020. You guys all, I think you all have smartphones. You all have access to the internet. Worst case, you go to the library. So you have Desmos to investigate. But let's show you how we get this. So if we go back to our original page, or our whiteboard, let me say that I paid attention when I was a little peasant, and I know that I can factor this, right? So I can write this as, pull out an x, and then this is the same as, I can rewrite it. This is 3 minus x. And this guy, I can also factor out at least an x. If I factor out an x, I'm left with 2x squared minus x minus 5. Now, this guy does not look like it factors anymore. I don't think I can, right? But that's okay. Here's what I know. I know I have a parabola, and I know exactly what it looks like. So without even using Desmos, I can reason this. Now, I'm not saying you have to use the same reasoning that I'm using, but it's never bad to sort of do these kinds of things. So if I come over here and I draw this picture, I can make a sketch of this region. Well, what do I mean by that? Well, let's get out, what color? Let's try to keep it consistent. The blue one was the cubic, so I think that's the case. Yeah. Blue was the cubic. So I'm going to stick with my red one first. I know right away that this red guy looks like this. I know it hits here, and I know it hits here. That's what I know for sure. And then I know it's a parabola that's upside down. So it's going to look like this. I'm just sketching the region. That's all I'm doing. Now, if I wanted to, I could use the quadratic formula to figure out where that cubic hits. I already know it hits at 0. So I know that that cubic has to touch here as well. But since I know the leading coefficient, what it is. I know what it is. It's positive, which tells me, I remember from my algebra days, that means it goes up and down and back up. You might remember in algebra, you study these things like end behavior of polynomials, or in like a pre-K, you might remember that. You should have studied it. So here's what I know. I know for a fact that this thing has to look like this. It has to come down like this and then go up. It has to. And then it has to come up like here and go down. Now, the only piece of information that I don't quite know yet is if these guys intersect down here. Now, I know it from looking at the graph, but I don't know that from just using some basic reasoning. So right now, I might think the only area that I'm interested in would be this region. This is clearly bounded by the two curves. Now, over here, nothing else is, because these things are going their separate ways. Is everybody okay with this region? It's definitely there. Okay. Now, how do I figure out, A, if these guys intersect down here in the lower left? How do I figure that out? And then how do I figure out this point of intersection? Well, Desmos kind of gave it away, but we can definitely solve these things. So let's note that we can do that. So to get intersection points, you just set them equal to each other and solve. So you solve negative x squared plus 3x equal to 2x cubed minus x squared minus 5x. And how do you solve this? Well, what I'm going to do is I'm going to take everything to one side. I'll put 0 on the left. This becomes 2x cubed. And then the x squareds do what? Cancel out. So when I take 3x to the other side, I get minus 8x. Negative 5 minus 3 is 8. And so, of course, now I can solve this. This becomes 0 equals, I'll pull out a 2x and I'm left with x squared minus 4. And so what we've just found are the intersection points. We already knew that they intersected at 0. But what is the solution here? The solutions here are x equals 0 and then plus or minus 2. So take a moment to convince yourself that I'm not lying to you, and convince yourself that you could have reasoned that on your own. Probably not as quick as I did, right? Yeah, you have a question?
Why did we do minus x squared plus 3x?
Because that's the expression. I want to know when these curves intersect. The curves intersect when their y values are the same. So I set one curve, y values equal to the other curve, and then I determine what values of x make that true. So yeah, if you ever when you want to know when two curves are intersecting, you set their y values to each other. So we set y equal to y, but each y has a different representation in there in terms of x. We solve it and we get 3 points. So here's what we know. We now know, for example, that this point right here, this guy right here is, you're going to plug in 2 into this. This is 2, comma. It doesn't really matter what the y value is, but it turns out that this is going to be 2, comma, 2. And then over here, we know that these guys do intersect. So I can come over here and modify this now. I'll kind of cheat. I'll make this look a little, again, I'm only sketching this. I just want to get an idea for what the region looks like. So it comes down like this, and then we know this point is negative 2, comma, Well, what happens when you plug -2 in? When you plug -2 into either one, for example, you plug it into the first one, you get -2, so you get 5 times -2, which is -10. So now I have 2 regions and I want to know the area, so that's what I'm going to do. And this region looks, again, I'm sketching it, but it looks like this. Does anybody have a comment or a question about this? So technically, a problem like this, the setup is what requires most of the effort. Yes?
So what you find is integration, use X when the bottom.
Yeah. You have to use X. You use the function. Right? What's the function here? The function is, y equals something in terms of X. So you're going to use X. Okay, so here's what we got. If we go to the next page, we're going to integrate it. But let me remind you that we have 2 integrals. The first one, the blue guy, the cubic is up top. And then for the second region, the cubic is now the bottom. So let's be very careful with this. So the area equals region 1 plus region 2. Again, emphasize that. So this is, we kind of didn't do any of the easier examples. We kind of jumped to one of the more challenging ones. But like they say, you don't get better playing against the JV. You got to play against the varsity. So what is region 1? Well, that is the integral from -2 to 0. And what was the top function? Well, remember, the top was the cubic. So the cubic was 2x cubed minus x squared minus 5x. And then you have to subtract off the bottom, which was the quadratic, and that was minus x squared plus 3x. So that's the first integral. And then this is plus the second integral, which will be from 0 to 2. And now we have to flip them. It will be -x squared plus 3x minus the bottom, which was the cubic now. So we have not done any calculus at all. That was the first calculus we did in this problem. And all we did was write calculus symbols. We haven't even done anything. So if you have something you want to say, this would be a good time to say it. Does anybody have a question or a comment? Yes.
How do you know which function?
How do I know which one's the top? So go back to the picture. Which one's bigger? In the first region, blue is above red, correct? So what's the blue one? The blue one's the cubic, so that's how I know that I'm going to put, this guy first. And then in the second region, the blue guy is the bottom, so that's why he gets underneath. So you take the top boundary minus the lower boundary. Okay, so now this is not a terribly difficult calculation because these things are going to simplify. If you do a little algebra, you have 2x cubed, then you're going to have -x squared plus x squared, so they cancel, and then you have -5x minus 3x, so you get this, minus 8x dx. And then the second one is going to clean up nice as well. You have -x squared, and then minus a minus is positive, so the x squareds cancel, and then minus a minus, and now you get 8x minus 2x cubed dx. So you want to check your algebra To make sure you don't make any errors, you got to distribute your minus signs, all that fun stuff. But now you have two, what we would say, elementary integrals. They're polynomials. So when I integrate the first one, 2x cubed, when I integrate that, that becomes 2 fourths x to the fourth. This becomes minus 8 over 2 x to the power 2, and this is evaluated from -2 to 0. And then the next one becomes very similarly 8/2 x squared minus 2 fourths x to the fourth. And this expression will be evaluated from 0 to 2. Now, the good news is when you plug in zeros, everything goes away. But there's another subtlety here that can really haunt you. It's that when I plug in 0, I get 0, but then it's minus what happens when I plug in -2. So it might take you guys a few steps to do this, but since we're running out of space, and I'll give you the algebra practice at home. First off, 2 fourths is 1/2, correct? And then -2 to the fourth power becomes +16. So this becomes, this is a scary thing. This becomes minus, this will be minus what happens when I plug in -2. So I get 32 fourths minus 32 halves. It's one way to think about it. And then over here, it's going to be plus what happens when I plug in 2. So when I plug in 2, it's going to just be the opposite. It's going to be 32 halves minus, well, 2 to the fourth is 16. So this becomes minus 32 fourths. And so what's the answer? Well, -32 fourths plus 32 fourths is 0, and plus or minus is 0. So this thing, we got 0, but that doesn't make any sense. Where did we go wrong? Actually, we don't. So what's the answer here? Okay, so -32 over 4, and you have 2 of them, so you have, so 32 over 4 is what?
16.
Yeah. Say that again?
16.
Yeah, okay, you're right. So what's 32 over 4? That's 8, right? So you have a -8 minus a -8 becomes -16, right? Okay, so first off, let's slow down, because I think what you're getting confused is you're doing different arithmetic. I'm doing them separately. I'm not, okay, so here, we'll just, and so we don't have to go to the next page. Let's go up here. So if we want to finish this, we have to go up here. What is this equal to? So you can, let's just go slow. It's minus, so you have inside here, you have 8 minus 16, right? And then over here, you have plus 16 minus 8. So what you end up with is what? So you have +8 here, +8 here, so you get 16. So what's interesting here is both of those pieces have the same exact area. So this is a challenging problem. It has a relatively difficult setup. It's not that the integration is hard, it's the arithmetic that can be issues in the algebra. So here, if you had to ask me my opinion, this is what makes this problem challenging is all, not the calculus, it's all the other stuff. And challenging might be a bad word, but what gives you all the places you could make an error is the algebra and the arithmetic. All right, does anybody want to say something about this before we move on? Good, because I wasn't going to say, no, just kidding. All right, so someone asked about 1G and H. Let's go back up to that one. Yeah.
When
For number 9?
Yeah, that's one.
Oh, that's a typo. That doesn't make any sense. Yeah, look, number 9's a typo. I got to fix that. That doesn't make any sense. That's nothing to do with the problem. I'll fix that. I don't know how that happened. Good catch. +5. Hey, don't forget, gang, we have class tomorrow. What time? Like 11:50 or something. That's a weird time. What's that?
I think it's from 11 to 12:45.
Yeah, something weird like that. No, it shouldn't be to 12:40. It should be 11:50 to 12. So it should be like 11:50 to 12:35 or something like that. I don't know. It's all weird. The corona's got us all mixed up this semester. Yeah, so there's a typo in 9. I'll fix that. Don't worry about it. All right, so someone said 1 G and H. Is that what we're at here? I have to look them up. We got multiple screens happening here. This is a good problem. Let's change colors. We've been using the black one. Let's go to the blue. I like the colors. That's the only benefit I like about using this thing is multiple colors. What do you prefer? I prefer the board moving around, but some of you might prefer this. I don't know. Yeah, so someone's a good question, Eric. Yeah, I just think we go Group A tomorrow. By the way, if anybody is going to Zoom all the time, or if anybody wants to try to come in person all the time, just shoot me an email and I'll try to make it work. Any of you can Zoom if you want. Just let me know, so if someone wants to come in and use your seat, I can let them know. Does that make sense? I got your email, by the way. I just haven't had a chance to get it yet. Okay, so this is number 1. I don't want to do the same one, but let's look at 1G. Similar to, at least. So let's, instead of it being sine to the 8th, for fun, let's say sine to the 5th. X, cosine of x dx. So what kind of thought process should you have with this? Well, what I would suggest you do is I would suggest anytime you have an integral, you need to come up with sort of a hierarchy of things you ask yourself. And every one of you might have a different thing. If you look in books, a lot of books will give you some little acronym for figuring out how to do this. I don't like to do that. I like to just think reasonably. And maybe that doesn't make any sense to you, but that's kind of how I like to do it. What I would encourage you to do is ask yourself, is it easy? Is it a fundamental thing? This is not fundamental. When I say fundamental, I mean something like a polynomial that is just direct. You have a rule. This one, I don't really see a rule, but what I do see, the first thing that stands out to me is I see a function and I see its derivative in the same integral. And anytime you see that, that should be like the red herring. Is that a phrase or something? That should be the thing that says to you, oh, substitution might be the key. And so then at that point, the only question becomes, what's the substitution? And if you think back on Tuesday, and in those of you who had me in the spring or in the summer, one of the things that I always suggest when you're not sure what to do and you have a composition, set whatever's in the grouping symbols to your new variable. Now, of course, you're going to say, I don't see grouping symbols. Well, but they're there. They're just not. They're not there. Because really what I'm doing is I'm taking sine. I have 5 of them. And I'm multiplying them together. So sine is actually grouped together. That is really sine to the 5th power. That means sine raised to the 5th power. So because of that, I am going to use the substitution. So the grouping something to the 5th suggests, and this doesn't always work, but it's going to work here. So it's going to suggest that I set y, or any letter, I don't care which letter you use, equal to the sine of x. So that dy dx is cosine of x. And what's fascinating about that is by the change of variables theorem, that tells us that dy is equal to the cosine of x dx. If I just rewrite those differentials. And so what looked like an ugly integral is actually going to simplify to a simple baby one. And again, I don't mean to say that to hurt your feelings like this is so easy, we call it baby. That's not what I mean. What I am trying to suggest is I'm suggesting that the goal of integration when you have a challenging integral is to somehow rewrite the original one as a known one. That's the goal as I take my multivitamin. Got to fight all the demons out there. You're like, that ain't a vitamin. That could be a narcotic. It is not. It is a men's multivitamin from General Nutrition, which I think just filed for bankruptcy. The corona has a lot of collateral damage, my friends. All right. So what do I mean that this becomes a baby integral? Well, when I plug this in, the integral of the sine to the power fifth of x, cosine of x dx becomes y to the fifth dy. That's it. And of course, this is 1/6 y to the power 6 plus c. And then the very last step we have to do is we have to get our original currency. Our original currency was x. So I'll replace y with what it's equal to in terms of x, and that is 6, sine of to the power 6. Now, you could verify this is correct by differentiating. You should do that. That would be good practice for you. Take the derivative of what we got at the bottom, and you'll see that it's sine to the power 5 times cosine. Some of you will get to see lots of integrals that look like this, depending on what your major is. If you guys are in engineering, you'll study these things called Fourier series and Fourier transforms, and you'll see all these integrals everywhere, and you'll be so mad that you didn't pay more attention to the bearded fat man named me. I know I should have listened to O'Grady. I knew it. He tried to get me. Even with our mask. This means, I was telling the other, well, we'll save the jokes for later. Questions about this? So what I want you to take from this is notice that power of 8 was immaterial. I don't care what number was there. The same strategy works. And if sine and cosine were flip-flopped, it would be very similar. You would just have a negative sign floating around. So that's how you do G. Does anybody have a question? All right, let's look at H, I believe someone asked. I think G and H, yeah. Let's check that one out. It's 258. We're moving along swell. We'll do this one precisely because I can't think off the top of my head how to switch it so that it works. So the trick here is to recognize, just like in the previous problem, that you have a grouping. It's just not as obvious what it is. But a fraction is a grouping. You're taking a numerator and you're dividing it by a denominator, whatever that means. And so what is this creature equal to? I ask myself right away, is it easy? And the answer is no, it is not easy. So then I say, what do I do? And one of the things I recognize, just like in the previous problem, is that I have a function and its derivative in the same integral. The numerator is the exact derivative of the denominator. And that's the sort of key observation to make. So the numerator is the derivative of the denominator. Now, of course, I could say that and you might believe me, but you don't understand the connection, and that's okay. But I'm trying to help you see that. So this suggests substitution. Notice I'm being very careful with my words. I'm not saying substitution will work, because it doesn't always work. but it's going to work here. And so let's use, what letter should we use? How about we used U, we used Y. Let's use a different letter. How about we use R? R seems like a good one. R equals 1 plus e to the x. Then dr dx is equal to e to the x. And so if we can take some sort of if you can kind of take this kind of stuff with you, or not with you, but if you trust me on the algebra, we can sort of go right to it. So what we know then is that our original integral simplifies to the known integral of 1 over r dr, which then becomes the natural log of the absolute value of r plus c. And of course, we can then write this as the natural log of 1 plus e to the x in quantity plus c. And that is the integral, which you can easily verify through differentiation. One thing you might say, why did you use absolute value in the one line and not in the next? Well, the absolute value is there in the first case because I don't know if r is positive or negative. But once I replace r with what it is, I do realize that it is now positive. So the absolute values are obsolete. They're redundant. Does that make sense? E to the x is always positive. 1 plus e to the x is always positive. And hence, we don't need the absolute value signs. You could write them there, but they're redundant. Does anybody have a question about this? These are fun. So wait a second. I got a question. You asked about 2b. Well, what did you do for 1c? It's the same problem. But you figured that out, right? Yeah, you got that one.
I didn't know that.
Oh, was a theta throwing you off? Yeah, you can use any letter. Okay, I see. That is true. When you're just like little babies, you guys. As soon as I use a different letter, everybody's like, "Huh? You can use any letter you want." You know, if I'm being silly, I mean, I could. You know, it sounds completely silly, but you know, I could have written. You know, for instance, like. You know, this integral, say, sine of 45x, which we showed you how to do, this is equal to the sine of 45t dt. I mean, they represent the same function, just the variable's different. And if you wanted to be nuts, you could say something like the sine of top hat x, or let me, no, not top hat, I did it backwards. You could say like sine of 45 square, d square, if you wanted to be silly, or you can say the integral sine of 45 top hat, magician hat, or you could say the integral of the sine of 45 cat, d cat. I mean, you understand what I'm saying? So the variable, we call these dummy variables. The variable doesn't change the actual structure of what you're doing. It doesn't change the function. Does that make sense? It's just, you know, we're so conditioned to think about x as the variable that it's hard for us when we start seeing other variables. But think in the real world, when you take physics and stuff, what is often the variable? It's t. Because often we're interested in what happens as time changes. Right? Make sense? Okay, cool. Any other questions on this homework? Yeah. Which one? Oh, E's a good one. Yeah, I'm surprised no one asked about that. How did you do it?
I did it, but then once I substituted 1 plus x, and then I found x to be the subject and replaced also the object.
Yeah, so there's a couple ways you can do this for E. Let's look at E and then we'll call it a day. How's that sound? So E is an interesting one because there's a couple ways to do it. So let's think about it. Let's try to do it two ways. We'll do it an algebraic way, and then we'll do a substitution. They're both really the same, but it seems that they're two different ways. So this is 1e. So this integral we're after is x over 1 plus x dx. So here's my first attempt. So what I'm going to do is I am going to do what you said. I'm going to try substitution. So I'm going to set u equal to 1 plus x. And then that means that du dx is equal to 1, right? Okay, so, so Folger, you got the other idea. The other trick is to do the zero trick, which we'll do next. One of the most famous tricks in all of math and science, adding zero. We'll show you that. So let's do it this way first, because this is the way you said you tried. Okay, so when I do that, it looks like I'm stuck because I get x over u, and then dx is just du, so it looks like I'm stuck with this x here. But I don't have to write x here. So let's back up and let's plug it in. And what you'll see is it actually falls right in your lap pretty easy. You get x over 1 plus x dx becomes, this just simplifies. So the thing I need you to do is I need you to look at your relationship between u and x. And this is something we often don't do, but this trick works sometimes. So we don't really call it a trick. We call it a method. I can rewrite this. What do I know from this relationship? I know that x is u minus 1, correct? So this means that I can write this as u minus 1 upstairs over u du, which at first glance you might say doesn't help, but then you remember what you learned in algebra class. This is u over u minus 1 over u, which is the integral of 1 minus 1 over u, which becomes u minus the natural log of the absolute value of u plus c. And if we plug our guys back in, we get 1 plus x minus the natural log of the absolute value of 1 plus x plus c. So that's one answer. So does anybody have any questions about this method? Does that make sense to everybody? Okay, so great. Now, one comment I can make, which I can either make it now or it's going to happen when we do it the alternate way, is you're going to say, if I do it the other way, I get a different answer, right? Or maybe you tried to check this answer in a computer and they gave you a different answer, or what seems different. So what will often happen is many times people will see how there's a 1 in that problem. In the front, it's 1 plus. A lot of times what people will do is they'll say, well, there's two constants there now. There's a c, whatever that is, and there's 1. So if I take two numbers and add them together, I get a new number. So why even write the 1 there? You could just take that 1 and throw it into the c, and then you just call it c again. Well, anyhow, we'll explain that a little differently next time. So does anybody have any questions about this? All right, anybody chatting that up? No, everybody chat. Cool. So let's do it another way. So let's do attempt 2. And now we're going to use the old favorite trick of adding 0. In a useful way. So the trick here is to look in the numerator and say, oh, I get it. I could take -1 plus 1 upstairs and write everything like this. Now you're going to say that looks silly, but I didn't change the value of anything, did I? I just wrote 0, but I wrote 0 as -1 plus 1. And now I'm going to do that algebra that I sort of did in the previous problem. It's going to look very similar because I can now write this as if I rewrite this, this is 1 plus x over 1 plus x minus 1 over 1 plus x. That's just some algebra. Now, if you're kind of confused if that's true, just reverse it. Just add them back together. They have the same denominator. Okay, now the left-hand term is just 1, so this is just 1 minus 1 over 1 plus x. And now we're in the almost identical thing as to last time, and you integrate this, you get x minus the natural log of 1 plus x plus c. And so what the amateur does is the amateur thinks that we're wrong, at least in one of them, because you're going to say the answers don't match. But they do match. Take the derivative here, you're going to get what you started with. Take the derivative on the previous page, you're going to get what you started with. So note, when you're computing an indefinite integral, you're not getting a function. You're getting a family of functions. It's an expression plus an arbitrary constant. Yes? It's not missing. That's what I was trying to tell you before. What's 1 plus a number? A new number, right? So what's 1 plus c? I don't know, some number. We could call it 1 plus c, or we could just call it c again. So that's a great observation, and you need to hit this very carefully. So note, 1, wrong button, 1 plus x minus the natural log of 1 plus x plus c equals x. I shouldn't say equals. That's a bad way of saying it. Because you might argue, but this is not bad to say. This thing is the same as x minus this. Why? The reason is because 1 plus c is also a constant. So we just call it c again. That's all. And we'll do that in some other instances this semester as well. It's a very useful thing to do. But either way, if you take either one of these expressions and differentiate it, what do you get? What you started with. All right, so we're supposed to be done at 3:15. It's 3:13. Does anybody have a question before we leave? Make sure if you're still stuck on some of these problems, we're going to learn something new tomorrow, but I'd be happy to do a problem or two. And if you're still stuck, reach out via email. I'll help you. All right, guys, thank you very much. I hope to see you tomorrow, and I will talk to you then. All right, take care, everybody. Thank you. Be safe.